This is lesson 2-4. We're talking about forces and vectors again. When forces act at different angles, the net or unbalanced force is the vector sum of all the forces. However, we have to use trigonometry to help us find the net force. So for example, if a box is sitting on a ramp or incline, the gravitational force, as you can see, is straight down. It moves towards the center of the earth. But this force can be resolved, this gravitational force can be resolved into two components. The perpendicular force, this is the box as it's pushing down on the ramp itself. What the ramp does, of course, Newton's third law says the ramp pushes back up with an equal and opposite force. But we call that force of the box pushing down on the ramp the perpendicular component of gravity, or sometimes just called the perpendicular force. All right, this little symbol here, it should look more like this. All right, it's just basically a straight line. And of course, we also have the perpendicular force pushing down into the incline, and then we have the parallel force which pushes down the incline. So one part of gravity pushes into the incline, the other one pushes down the incline. All right, and we call that the parallel force. All right, pushing down the incline, and there you have it. We've drawn it in two parts. What it does here is it just completes this right angle triangle. We've taken the force of gravity and resolved it into two perpendicular components. And again, these components are independent of each other. And the perpendicular force is balanced by the force pushing back, which is called the normal force. All right? So the normal force and the perpendicular force are equal in opposite directions. So we'll deal with these three forces, that is the force of gravity, and then of course the perpendicular and parallel force, and we'll also look at perhaps a little bit of friction that might be involved in a problem or two. So note that the parallel force and perpendicular force are the arms of a right angle triangle. You can see that there is a perpendicular force, there is a parallel force, and of course they are the arms of the hypotenuse, which in this case is the gravitational force. So the parallel force of gravity causes the box to move down the ramp. Friction may be enough to retard the motion a bit or entirely. If the box wants to move down, then friction is going to be moving in this direction, or it's going to be exerted in that direction to oppose the motion. And the net force is going to be the vector sum of those two forces. All right. Of course, if somebody's also pushing on the box at the same time, that can also be incorporated. So the net force on the box can be determined and then used to determine the acceleration of the box. So you would first find the net force, which is of course the sum of the parallel force pushing down, any applied force, whether you're pushing up or down, and then of course friction, which is going to oppose the motion. So if the overall force seems to be in one direction and starts the box moving, friction is going to oppose that. And whatever these three add up to, that's going to give you the net force, and the net force divided by the mass will give you acceleration. So here's a basic example. A force up a ramp is 200 newtons. So a force of 200 newtons is applied on a crate which has a mass of 20 kilograms. The crate is initially at rest with an angle of 35 degrees, and the force of friction is 32 newtons. What is the net force? What is the acceleration? And what is the final speed after 3 seconds? So the answers are given there, and what you should take a look at is see if you can figure out how to determine, of course, what the net force is. Well, the net force, remember, is just the sum of any forces that are acting. And of course, in this case, there are three. There's the parallel component of gravity. Now, the way you get the parallel component of gravity is you would take the angle of 35 degrees. So here's your angle. And if this is an angle of 35, then what you can do is find the parallel component of gravity, and we'll show you how to do that on the next slide. Now, once you know what the parallel force is, then of course you know that the applied force is 200. And of course you also know that the frictional force is 32. And so what you would do is say, all right, well, these are the two forces, the frictional force and the parallel force. They are adding against you. They are conspiring, if you like, against you. You're trying to push up with a force of 200 newtons. That's your applied force. That goes here. And whatever these two opposing forces are, you would find the net force by saying, all right, the net force is equal to, again, the parallel force, which is going to be, I suppose, negative, the applied force, which will be positive because it's up, and friction is going to also be negative because it opposes. So once you've added those three together, then you divide by, and you will get your acceleration. And once you know the acceleration, and you know the time of 3 seconds and the initial velocity of 0, you can calculate the final velocity. So we'll take a look at that, all right, in the solution. And it says step 1 is to determine the parallel force of gravity. And the parallel force is the force of gravity, which is, of course, the weight of the object, 20 kilograms times 9.81 meters per second, or it's about 192 newtons. We have to multiply that, though, by the sine of 35. Since the angle is 35, the parallel force is the sine. F parallel is mg sine theta. The perpendicular would be mg cos theta. So 20 times 9.81, that's the weight, times the sine of 35, gives you a parallel force, that is the force pushing down, of 112. And remember, your force up the ramp is 20. All right, but you also have the 32 newtons of friction. So we can use those three, though, the 200 plus the 32 plus the 112 to figure out our net force. So step 2, determine the net force on the crate. Net force is applied plus parallel plus friction, positive 200, because the positive, or the 200, is up the ramp. And then you add the two negative forces, the negative force of the parallel component of gravity and the negative frictional force, giving you a net force of 55.46 newtons. All right, and so that is your net force. So we've answered the first part of the question. Now the next step, step number 3, now that we have the net force, we acceleration. Acceleration is determined by using Newton's second law. We take our net force of 55.46 and we divide by the mass of the block, or the crate. And of course the mass of the crate is 20 kilograms. 55.46 divided by 20 gives us a net acceleration of 2.77 meters per second squared up the ramp. So your pushing of 200 results in a net acceleration of 2.77. And so now that we know the acceleration and we know the initial velocity and we know the time is 3 seconds, we can calculate the final velocity. All right? Final velocity is our unknown. We know what the initial velocity is. We know that the time is 3 seconds, and we determined the acceleration a little earlier. It's 2.77. So we manipulate our formula for VF, VI plus AT. Initial velocity was rest, or 0. Our acceleration times our time gives us our final speed, or velocity, up the ramp, 8.32 seconds. So after 3.0 seconds, the force changes the velocity from 0 to 8.32 meters per second up the ramp. And so that's the first example using the components of gravity on a ramp. Right? So you might see a question like that in Physics 20. Not too much of this would carry over to the 30 level, but it is important that you can resolve vectors into their components and then use those components. So this is a good example of a skill that we do develop quite a bit in 20.